Hardware interrupt measurement using STM32F103C8T6 Blue Pill Development Kit. Hi everyone, my name is Dr. Konark Sharma. In this lecture, we will learn a step-by-step approach of hardware interrupt measurement using an ARM-based STM32F103C8T6 Microcontroller on a Blue Pill Development Kit from Konark Sharma and Urvashi Srivastav. Here in this project, for understanding the interrupts in STM32F103C8T6 microcontroller, we used stepper motor as an external hardware interrupt. Upon completion of this lecture, learners will be able to understand how to use STM32 Cube IDE to program the STM32 microcontroller for hardware interrupt measurement using an ARM-based STM32F103C8T6 microcontroller on a Blue Pill development kit. So let's get it started.
KONARK'S research. Subscribe now.
Welcome. We now begin with the close-up of STM32 Blue Pill development board, which is neatly placed on the workstation. We are going to select our board microcontroller, which is STM32F103C8T6. Going to name our project as bluepill_hardware_example. We are going to select our targeted language in which our code is going to proceed as C++. Now, we know hardware interrupt masking is a process of enabling or disabling hardware interrupts in a microcontroller or a process so that only selected interrupts are allowed to be processed at a given time. On the screen, we have STM32 pin configuration. We are going to select our RCC high speed clock cycle, and we are going to select the high speed cycle and going to give it 72 MHz of this clock pulse. Hardware interrupt is a signal from a hardware device like timer, keyboard or sensor to the CPU, telling it to pause the current execution and run a special function called ISR, interrupt surface routine. Masking. To mask an interrupt means to disable it. The CPU will ignore it. On the screen, we are using our debug mode as serial wire, and we are using pin PB10, PB11, which is pulse width modulation pulse. What is the need of interrupt masking? To prioritize some interrupts over other, to avoid nested interrupts that might cause bugs, stack overflow, to protect critical code section from being interrupted. Now, we are device configuring a tool that is updating our code present in C++ language. This is the code present on our screen, in which we have our main.h file that includes a template of a code. We are building our project, which is built around 20%. In STM32, for protection of critical code section, we use our interrupt masking. Here we have our code in which we are going to write in this code section we are going to write our code from volatile int32. The section of code is an STM32 Hall-based GPIO interrupt program using PB10, PB11. The volatile int _t steps equals to 0. int32 is a 32-bit signed integer ranging from -1 -21474866648 to the positive 1. Volatile tells the compiler not to optimize this variable because its value can change unexpectedly, i.e. inside an interrupt. We initializes the counter. This variable tracks steps for a motor or encoder, and it's updated inside an interrupt. For this code, Hall_NIVC, we set our priority to the exit line 10 to 15 with the highest level to 0. Enables the interrupt request to those which include PB10 and PB11. The void Hall_GPIO exit_callback program. This is a user-defined callback function automatically called when an external interrupt occurs. We check if the interrupt was triggered by pin PB11. We read the logic on the pin PB10. Step ++ if PB is high increments the steps. Step - if PB10 is low decrease the step. Summary of the code is an interrupt occurs on PB11, likely and press button. At that moment, PB10 is checked. If PB10 is high, step forward, and if PB10 is low, we step backwards. This is commonly used in rotary encoders, motor control, step counting, and in applications like robotics. Next, when the Hall GPIO exit callback is triggered, the code will check PB10 state and updates the step counter accordingly. We can use steps variable in main to display position, to control motor output, to track rotation or movement. We can see tire being rotated by us. So when motors are involved, the code is often to track movement, direction, speed for this motor to generate signals like pulse or wire to GPIO interrupt pins of a microcontroller. A rotary encoder is attached to the motor shaft, which have output two channels usually called A and B. These are square waves on 90 degrees which are out of phase for quadrature signal. These signals are connected to GPIO pins, say PB10 or PB11. PB11 is used to trigger an input for a rising edge like we are doing so, and we are getting value of 677 with the range of the int 32 sign bit, and it can go to the value we have decided. Thank you.
Finally, we would like to cooperate with you according to the best of our knowledge. Keep your feedback and suggestions coming. They help us to provide you quality work that resonates with your needs and requirements. Thanks much for sharing your kind suggestions. Keep healthy, keep learning, and keep growing.
KONARK'S research. Subscribe now.